Gas turbine cycle part 2. So in this video, I'm going to explain about the Brayton cycle. Brayton cycle, gas turbine engine evolution. Okay, now we look into this engine evolution. First, it was proposed by George Bailey Brayton for use in the reciprocating oil burning engine, and he developed it around 1870s. However, today it is being used for gas turbine. And as you can see, the compression expansion process take place in the rotating machine. So as your attendance, please write who is Bailey, who designed this Brayton cycle. Brayton cycle gas turbine. So first we look into the actual uh, gas turbine engine. So we have two gas turbine engine. So in the gas turbine engine, we should identify the component. First is the low pressure compressor, and same with the other one. And so we have high pressure compressor, and we also have the combustor. And now it goes to the high pressure turbine and also low pressure turbine. So this is the actual diagram of simplified from the actual system of the gas turbine. So actual gas turbine engine cycle, as you can see, it comes from fresh air. First at the state 1, fresh air. It goes into the compressor here, and output of it is the high pressure air. And we have fuel intake into the combustion chamber here, and the products goes to the state 3, generate or will propel this turbine and generate work net out, and the exhaust is state 4, which is the exhaust product of it. This is the actual simplified from the actual system of the gas turbine. However, by using the extended assumption, the cycle turned out to be a closed loop system, a closed loop cycle. And as you can see, start from process 1, goes to the compressor, and it goes to state 2, then goes into the heat exchanger, constant pressure heat addition, and it goes to state 3, generate the turbine and generate work net out, goes to state 4, and constant heat rejection process, it goes to back to the state 1. So this is the Brayton cycle by using the extended assumptions. Closed cycle gas turbine plant. So Paris 1952 is the citation, and this is the 3D view of the gas turbine plant. And from the actual gas turbine engine cycle, simplify of it. From this figure, which is from the 3D view, you should be able to identify which is compressor and which is turbine. So as you can see here, from this arrow, so the arrow goes in, and then the symbol or the diagram is the same as the compressor. So the air goes in at the large surface area. Okay, so this is larger than this. So it goes into the large, and the output is at the small area, meaning that the pressure is increasing. So that is why it being called a compressor, and why the symbol is look like this. Okay, so based on this, we can know that this is the low pressure compressor, and we also know this is the another compressor, which is the medium pressure compressor. Okay, so the intake here, output here, and then another one is the high pressure compressor here, intake and outlet. So, and then we also can know which one is the turbine. So as you can see, this is the high pressure turbine. The intake as the small area, it goes out at the large area. So from this symbol, we will know that which one is turbine and which one is the compressor from the intake and outlet, inlet and outlet of the air. And this is another one, which is the high pressure turbine. And we also, from this figure also, we can know which one is the combustion chamber or the boiler. So this is the air heater and also the combustion chamber here. So this is the main component of this uh, closed cycle gas turbine plant. So if we know all these components, we can calculate the efficiency of the plant based on the pressure and also temperature. Closed cycle gas turbine plant flow diagram. So in the previous slide, we look into the 3D diagram, 3D diagram. Now we look into the flow diagram. So this is the simplification of the 3D diagram. And as you can see, this is the low pressure compressor, LC, and medium pressure compressor, MC, and we have HC high pressure compressor here. We have two high pressure compressor, HC1 and HC2. And as you can see the direction of the arrow, so it comes from here and it goes to this here and goes here, and so this is the direction of this arrow and it goes to the, yes. Now we look into the low pressure turbine, LT1. So this is the LT1, and the opposite of it goes back into the passenger. Okay, high pressure turbine. So this is the high pressure turbine, goes back to this here, and AH, air heater or combustion chamber here, and generator, starting motor. So this is the generator, and M is the starting motor, recirculation blower, intercooler, pre-cooler, regenerator, recuperator, air preheater, charging blower, and exhaust gas turbine, ET. MG motor generator. So from this diagram, you already know which is the main component here. This is the main component here, and this is another main component here, and also this is the heat exchanger or the uh, combustion chamber. So based on just simple diagram, you can calculate everything if you know the pressure and the temperature. The main components of gas turbine plant, compressor and turbine. So this is the cross section of the gas turbine engine, and as you can see, this is the low pressure compressor, and this is the high pressure compressor, turbine, and this is the actual diagram of it, compressor, turbine. And the same goes to this figure. We have a low pressure compressor, high pressure compressor, and high pressure turbine and low pressure turbine. So based on this diagram, you should identify which one is turbine and which one is the compressor. The main component of gas turbine plant, combustion chamber or air heater direct. So this is the cross section of the gas turbine, and as you can see, this is the compressor rotor, and this is the combustion chamber, turbine rotor, and the air will goes into the compressor rotor from okay, here is where air will goes into the uh, compressor, and the air will goes into the compressor, will be compressed by the compressor. The output of it will goes into the combustion chamber here, and the combustion chamber, the fuel will be injected into the combustion chamber, and the combustion will occur here, and the combustion products will propel the turbine, and turbine will move the air to the surrounding or outside of the process or the system, and we will generate the turbine. The exhaust, the product of this is the exhaust gas or the combustion products. So this is the complete system of the gas turbine plant. Brayton cycle. Now we look into the Brayton cycle. So we use the ideal cycle for the gas turbine engine, as you can see, based on the standard assumption and so on and so forth. So this is the PV diagram of the gas Brayton cycle. So PV diagram, and we have two isentropic process 1 to 2 and process 3 to 4. And this is the TS diagram. We have two process of constant heat addition process and heat rejection process from process 2 to 3 and process 4 to 1. And this is the simplified diagram of the actual gas turbine engine cycle. However, in this analysis, we use the Brayton cycle based on the air standard assumption. And the process in the Brayton cycle, first is the isentropic compression, process 1 to 2. And then it goes to the constant pressure heat addition, process 2 to 3. And goes to the isentropic expansion, process 3 to 4. And constant pressure heat rejection, process 4 to 1. So this is the complete process of the Brayton cycle. And we assume that the system is steady flow process, so we neglect the kinetic and potential energy. So based on this, the energy equation for the open system is Q in minus Q out plus work in minus work out, and it is equal to H exit minus H inlet. So this is the energy equation for the Brayton cycle. This is the end of part 2 for chapter 3. Hopefully you enjoyed this video, and thank you.